Good morning, everyone. Thank you all for coming over to watch my presentation. My name is Linfeng. I've had pleasure being a summer intern here. I'm excited to share my work I have been working on the acceleration of thermodynamics module in MagPi using C++. So here's the big picture. The main motivation for this project is to improve the performance of complex calculation with a primary focus on the CAPE function, which is convective available potential energy. So as you can see in this QT plot, well, the CAPE calculation is not a single step process. Well, it is a multi-stage process that relies on several different key thermodynamics building blocks. For example, we need to find the LCL level, and also we need to calculate the dry lapse and moist lapse profile, and using them to concatenate a parcel profile. And then we also need to find the intersections between the parcel lifting profile and the temperature, environment temperature profile, which are the RF and the EL level. Um, and finally, we need to do the integration of the area between the two profiles. So this is all these steps, especially when dealing with large and multi-dimensional data sets, can be computationally intense in Python. So that's the core problem I need to tackle. So the main tool I'm using is a C++ library called Python 11. For those who are not familiar with it, it is a lightweight C++ library that can be easily exposed to Python. So it's a bridge between C++ and the Python world. Here you can see a very simple example, the add function with only a couple of lines of code. This function can be called by users using a Python interface, but it's actually running in a C++ function. So at the very beginning, I simply thought it's just rewriting everything into C++ and expose them to Python. But after converting several thermodynamics function, I realized it's not that straightforward. So there are a couple of different aspects I need to think about. The first thing is the units, how to deal with units in C++. And the other thing is I need to check the input. If the input is valid, is it scalar or array input? And in some cases, we also need to broadcast the array into a higher dimension. And also, we have all the constants already built in Python, but we need to retrieve them and use them in C++ function. And this is the core section, is the computing. And finally, sometimes we need to assemble different values together to give the user a collection of values instead of just a simple value. So we can first take a look at this example, the function of saturation vapor pressure. It has a pretty important logic which handling different phase for the values. For example, we have liquid phase or solid phase, and also the automatically determined by the program. So in this case, my first idea is just to passing everything into C++ and let it to determine if we need to use the liquid function or the solid phase function. This is a pretty simple implementation, but if we think about it, it can also be a good idea if we keep the Python to determine which phase function to choose. and then passing all the values to C++ to do its specialized computing work. But here comes another problem is because sometimes we have other C++ functions that need to call for example, call the saturation vapor pressure here. So to solve this, I need to add another C++ function, which can caters all the other C++ internal friends, such as the saturation mixing ratio, which call it. So this is basically an idea that can apply to all the following work, which is we have a C++ version and a Python version. The Python can deal with user-facing logics, while the C++ level dealing with all the interaction within the C++ world. And here is another example, which is the parcel profile helper function. So it is a function that gives you three important components when you are calculating a parcel profile lifting from the like surface. Uh, it gives you a dry adiabatic profile and moist adiabatic profile, and also the LCL level between these two profiles. While the other two function, parcel profile and parcel profile with LCL, sorry, they call the helper function grab the things together and determine how to piece them together in different way. So in this case, we also have two different implementation, either putting the assembly work in C++ or in the Python. But here, considering that the helper function returns a very complex data structure instead of a single value or a single array. So it would be better to keep this thing in Python because in Python we only need a couple of lines of words to concatenate things together. But if you want to do it in C++, it's gonna be a lot of headaches dealing with memory allocation and things like that. So I just put the assembly work here in Python. And now we move on to another important implementation, which is determine where the vectorization should happen in the code design. For example, all the C++ function I'm writing is a scalar function, which means it takes a single value as input, like it takes one pressure and one temperature, and returns only one scalar value. But when it is exposed to Python, we need to vectorize it so that user can work with array input. This is called the Python 11 API vectorization. On the other hand, for example, this scalar function can be directly called by a higher level C++ function to produce a 1D dry profile, which can then be a very important part in the parcel profile helper. So this is the internal C++ vectorization. Both of these two kinds of vectorization happens in my code design here. So we take a closer look. This is a pretty useful utility to do the work provided by Python 11. It's directly operate on the scalar function, for example, the dew point, and only a couple of lines of code, it can be exposed to Python. So you can see the example if you have array input, the array is passed to the C++ level and all the looping happens in the C++ side. It is also crunched down into the very tight and optimized loop by the C++ compiler. But the pi vectorized operator also have some limitation. For example, we have a function called calculating the LCL level. It is special because this function returns two different values, which is the pressure and the temperature of LCL level. In this case, it cannot work very well with pi vectorized. So I need to write manually a ramper function, which call the LCL function directly. And with the help of this ramper function, the user can also pass in a multi-dimensional data, and it can uh, loop over the scalar function to get results for each value. So putting all things together, this is basically the architecture for calculating the CAPE function. As you can see here, it's a pretty intertwined deep tree of all the interactions and dependencies. And you can also notice we have some other bottom level C++ functions, for example, specific humidity from dew point, like moist air specific heat. All these functions actually has been exposed to Python level and can be called through a Python interface, but it's just due to the limited room here, the connection is not shown. Um, and then to measure the performance of this new architecture, I use the ASV. ASV is a very useful benchmarking tool that can work with Python. So as you can see in this table, we have the EL function, LFC function, and also like parcel profile function. They have gained a very significant reduction in running time. Some of them even reach 50% of reduction. And also like the Morse labs calculation for 1D array, it's even reached 90% reduction. But you may also notice there are some challenge for the dry labs function, the which consume more time when calculating. So let's take a closer look. I have been trying to pass a broadcast array or a hard code array into the dry labs function. So they both work pretty well for a 1D array input, but for a 2D or 3D array input, the C++ version kind of consuming even 15 times more time. This can imply that the Python is pretty efficiently handling its Python own broadcasted array. While the broadcast array is passed into C++, it kind of drag everything slowly. So, but compared to that, if we give it a hard code array, it has a pretty good improvement, like a little bit of improvement in the runtime consumption for 1D and 2D, but for 3D, it's still gonna take half more time. So at this stage, we might still allow user to use the Python version dry-labs function, while the C++ version can remain in its C++ internal calling. So that's basically all the thing about the MatPy project, and there are still a lot of things to do in the future. For example, the first one is you may have noticed, besides all the thermodynamics function, we have a couple of math function, like the trapezoid is integration and the fine intersection is also dealing with some math and logic things. Both of them are very important part under the CAPE calculation. So uh, they uh, they are kind of out of my scope right now, but we can probably look at it in the future. and I believe this can significantly speed up the calculation. And also another thing is, um, you may have noticed here, the cape function is directly calling the LCL, while it is also indirectly calling it through LC, EL function, and also the parcel profile function. So this can be a huge uh, obstacle that can make the runtime even longer. So we probably, if we can only call the LCL once, it would be better and speed up everything. And also, of course, we need to resolve the dry labs issue. And another thing is the parcel profile have I have already have a write a C++ version of parcel profile helper, even though it is not right now connected with other functions. So it's just halfway finished. Um, and finally, it's just we have already touched down to the main tree of K calculation, but there are still also a lot of other functions that serve like surrounding the main calculation that we can look at it to move it into C++ level to speed more things, speed them up. And that's all things about the MatPy project. And I have some other things to show you guys, which is very interesting here. So I've also been working with Yuan and Sean to visualize the Jupyter simulation in an integrated data viewer. So I got a data set from someone else um, who is our collaborator, and his simulation data is in beta plan, and we have a very um, fine grade resolution for this data set. And the pressure levels, like from zero point 1 to 80 bars, is pretty deep, from shallow level to deep level on Jupyter. And it has a latitude and longitude range about 50-degree range. So you can see here is a simulation of the all structures on Jupiter's surface. You can clearly see the vortices and the plume traveling eastward, and also the characteristic band and zone structure. Here's some part of traveling east, some part of traveling west, and here you can see this is some very interesting simulation made by Yuan. Uh, You can see they are displayed by different variables. Some are displayed by wind speed, some are relative vorticities that can give us a pretty good view of the uh, vortices structure. You can see here, this is a vortices traveling eastward, following by a chain of other vortices. And also here I visualized the you can see on the top image, top video. This is the cloud structure. Uh, and also here is the relative vorticity. So the vortices basically they occur at around 0.1 bar pressure level, but you can see it has extended very deeply into around 85 bar pressure level. So actually, this is a like a whole structure stretching from the surface to very deep below the surface. So some simple images. Here is the relative vorticity and the shallow level and the deep level. So the IDV has a pretty potential in visualize things in other planets. Although we have struggled a lot in dealing with the data format and also this stretching things so that it can better align with the um, Earth-sized globe. Because Jupiter is like even several times bigger than Earth, so we need to move everything align well with the background globe. Yeah, and I really appreciate all the help from my colleagues here. Without you guys' help, I cannot make it through the summer. Yeah, this is a very cute I should also put away when I commute here. So with all these photographs I have been taking here, I'm welcoming any questions.
These photographs are lovely.
Yeah, thank you. Practicing my skills.
If we have questions from folks who are dialed in remotely, raise your hand in Google Meet and I'll call on you. Otherwise, in the room,
I have a question.
Julian.
For the wind speed ISO service, what kind of speeds are we talking here?
I think this is the yeah, I think it's you calculate the speed based on the speed in the three direction. You calculate the whole speed.
Only to the only the
So
UFB. We do not consider the vertical.
But I think he was asking about the magnitude.
Oh, magnitude. I don't know about
I
magnitude.
think it's for a typical jet stream on Jupiter, it's around it can reach even like 100 kilometers per hour or 200 kilometers per hour.
Yeah, one thing Linfeng not showing here is that we have put one of the, I think the first one of what testing or something like that to the Gemini. Also to the Gemini animation, and Gemini can actually recognize the vertices and all those kind of information revealed. They're quite interesting.
Yeah, Gemini can kind of recognize it, give us some its analysis, even though probably not that's accurate, but we still need to provide it with more information so that it can give us more idea.
What about other LLMs?
Other one.
Other large language models? I mean, you said Gemini.
The Gemini,
The other,
first,
you have Claude, you have.
yeah, Gemini is free first. The second Gemini is I think one or two. And can do the movie. You can upload movie. Most of the like the ChatGPT, I'm not sure. The free version, at least you cannot do that. This kind of stuff.
And just in this morning, I got an image from the guy who shared me his face. So actually, they are simulating a phenomenon on Jupiter here. So if you take a closer look, actually, we have just spot this phenomenon happening on Jupiter, which is a consecutive of several vortices traveling to the east. And you can see at the beginning here, it's only one vortex, and it's when it's evolving and traveling to the east, it gradually become larger and followed by a series of vortices, which is exactly the same as their simulation. Yeah, so you can see this structure. This is the first vortex and followed by a few different vortices. Or even in this image. Yeah, I think this is pretty impressive.
I have a quick science question. What's the driving force of these circulations on Jupiter? Is it just its internal temperature?
I think it's driving by based on the information they inform me. It's they have some what's called that name. It's some instability caused by the water and ammonia, vaporization and condensation. So that can trigger some kind of instability between the higher latitude and the lower latitude. So that between the two different latitudes, they can trigger the vortices moving in one direction. Yeah, if you remove the ammonia condensation, this phenomenon cannot happen.
Interesting.
Yeah, I think it's time to pass to Jay.
Yeah, if there are any other questions, we could have time for a little more, but
If we could have time, I'll sneak in a more general question. Just this summer, I'm curious, what is just one thing you learned this summer that you like would be excited to tell us or someone else you meet after the internship? And was there anything you ran into this summer with either of these projects that was stubborn or frustrating or a bit of a headache?
Yeah, I think the most exciting thing is that this is the first time I write a whole bunch of code in C++, which really improved my skill in this, and I can move this into more of other projects. Because in a lot of simulation and dynamic model, I also need to write C++. This is super helpful, and I can kind of combine the IDV project here with my simulation work. Yeah, I'm very happy to learn all these things during this summer here.
Thanks for that.
Yeah.
Thank you, and we're glad to have you here. I have a question for the Python team. Is it this combining Python with C++ a thing?
Yeah,
It's
in fact, we're leveraging heavily a library. Python 11s came out of the community that is regularly used. So the plotting library is Matplotlib, uses that a lot. Some of the like SciPy to wrap some algorithms uses that a lot. So it's been pretty battle tested. And actually a lot of the newer features on the C++ side of things has actually come along to reduce the amount of boilerplate you need to write. And so that's kind of Rust would be the cutting edge of things. We elected not to go there since the build chain's still a little and stick with the C++ side of things, which has been pretty robust, I'd say, so far.
whether C++ or otherwise, that was, I think, maybe the core of the proposal that they have both been contributing to this summer was how do we modularize the slow parses of NetPy and take it out of Python speed them. So definitely is a thing that definitely is and will be helping us out.
And is it through kind of trial and error and testing where you decide to do this combination or your priority based on past
There's
conversations of
a degree of knowledge from input from community, but also I think, especially with Ryan's experience, just a general understanding of the limitations of Python and NumPy, where they do slow down and when we have quantified them. CAPE is a high value function for us and that it is very highly used by our community. And we know that it hits those known limitations of Python and NumPy in the ways that we're using it. We are relying on a lot of explicit loops and calculating integrals at each stage. And that I think Ryan shared on a meeting last week that we had a community member say they tried to use our CAPE calculation, but they wanted to use it on a big data set. It took them hours, like on the scope of a work day to get this to run. And so that is where some of the compiled languages like C++ and Rust can excel in those sorts of tight calculations that can loop much more quickly. And so we knew a good place to start was high use, hitting known limitations, and then Jay will get to talk about quantifying and seeing the improvements when we tested this out.
Yeah, start with the idea that maybe we discover some more bottlenecks, but once you start with CAPE, as you saw from Linfeng's diagram, there's a whole tree of dependencies in there once you want to run CAPE with our existing set of thermal functions. So that and necessitated a whole lot of things that the leaf nodes to build up to getting to close to CAPE.
Does it parallelize or is that not?
Part of the goal of it was to enable using things like DAS for parallelization, but we're not using it internally. Like if you chunk it up and use DAS, that is a user problem and not a us problem, because just testing that and spinning up clusters to do, I don't want to integrate distributed computing into my continuous integration system. I have enough problems in my life.
What about the C++ level and parallelizing it amongst the core?
If you can distribute the kernel across your nodes, there's no reason that couldn't work on the chunks you're giving it, just like that Python function.
Another comment, is it possible not just limit to C++? Can you thinking about the Java? Is it possible? Because from Java version, the with IDV calculate came very efficient, pretty quick. I don't know the speed is comparable or not, but if that is possible, we maybe have some tests to see the performance.
Right now, not looking at the challenge with Java is then you have to instantiate a JVM. You have to manage that separate environment and everything. When you're doing C++ or Rust or C or even Fortran for that matter, all you have to do is get it compiled to machine code, which is part of your build process, and then you're deploying that within the existing packaging infrastructure for Python, which handles pre-compiled libraries. Java would be trying to deploy an entire runtime environment from within Python, which there is no.
Which can be more modularized.
Well, I'm sure it can be modularized more, but there's not a lot of existing things. So we'd be blazing our own path there. So we haven't been taking on the Java side of things there. Need to get on to Jay here.
Well, thank you again, I think.